Hi, I'm Rebecca Wright, Director of Computer Science at Barnard, and happy to welcome you here today for a computer science seminar, and especially happy to welcome our speaker, Professor Tal Rabin of the University of Pennsylvania. Tal is the Radcliffe Family Professor of Computer Science at University of Pennsylvania. She was previously head of research at the Algorand Foundation, and prior to that for 23 years at IBM Research as a distinguished research staff member, as well as the manager of the Cryptographic Research Group. She has made seminal contributions in the areas of security, multi-party computation, threshold cryptography, and proactive security, and more recently has been exploring how to use these methods in blockchain technology. Among many interesting and important service roles, she founded the Women in Theory Workshop, a biennial event for graduate students in the theory of computer science, and she also serves as the chair of the ACM SIGACT Executive Board. Tal has been widely recognized for her work, including as an ACM Fellow, an IACR Fellow, and a member of the American Academy of Arts and Sciences. She received the RSA Award for Excellence in the Field of Mathematics, the 30-year Test of Time Award at Stock, and the Anita Borg Women of Vision Award. She was also named by Forbes in 2018 as one of the top 50 women in tech in the world, and was ranked in 2015 by Business Insider as the #4 on the 22 most powerful women engineers. So we are thrilled to have her talking to us today about her work on threshold cryptography, from private federated learning to protecting your cryptocurrency.
Thanks, Rebecca. We have to get rid of this. I think it's over there. Rebecca mentioned the Women in Theory, so I just want to say we had a fantastic video from Women in Theory in the time where we couldn't have the conference because of COVID, and Rebecca starts it off by playing on the piano, so it's really a worthwhile video to see. The audience is a little bit inappropriate at the talk. Rebecca told me to do a general audience talk because there will be students, so it might. Thank you. Thank you. Thank you for validating my level of talk. Okay. When I was thinking what I would talk about, I, of course, wanted to do some work that I've worked on throughout many, many years. And I thought how I would present it, but also to give new things. And suddenly I realized that the problems that I'm working on, even if they're completely unrelated to the cryptographic techniques that I've developed and designed in the past, they utilize these techniques in a very interesting way. So I'm going to start, in fact, by talking about two applications where we use these techniques of threshold cryptography. At the beginning, it's going to be unclear, especially for the federated learning example that I'm going to give, how it hooks up into the cryptography, but you will see later at the end. So I'm going to start by describing the federated learning problem that we were looking at, then at the other problem of protecting your cryptocurrencies, and then I will start describing the threshold cryptography and sort of tying everything, hopefully in a nice bow together. Okay, so the federated learning is something that appeared in a paper that is called Flamingo. And what it wants to achieve is a secure aggregation system for federated learning with multi-iterations and one-time setup. Okay. Let's start slowly and get where we need to go.
It's like the New York Times spelling bee thing where you have to like put the letters together in the right order.
Okay, so I have to tell you something. Of course, it's not in the order, the thing, but wait till you get to the next acronym, which is PRINT, that has no connection, but is also an acronym. So somehow our acronym choosing abilities is deteriorating, but okay. So I want to start with federated learning to say what the scenario is of what we want to achieve. And this is, in fact, I put JP Morgan here because this is, in fact, work that has been done with JP Morgan. They funded this work and it's under a grant. And they came with a problem and with a challenge and things that actually interest them of problems that they want to solve. So they have many clients, and they want to, that are represented by your phone when you contact them, or maybe you're working off a laptop or a server. It could be all kinds of machines here. You can see the variation. And they want to learn some information to run some model on these distributed entities and to improve their ability to do various tasks. So, so then each device has its own machine learning model, and they can compute their local model and then send it to the server with the bank, and the bank can just compute some function over all these local models. Let's say an average, doesn't matter, but whatever it is. Okay, so this is a solution, but these things are sent in the clear, these calculations. If they're sent in the clear, then you can infer individual information about the weights of the clients. And many clients may not want to share this information. And it can expose things maybe about their accounts and so on. So of course, this is highly sensitive information. You don't want to do this thing. So the question is it really a solution? And the answer is no. Really what we want to do is we want to do some secure aggregation of the data so that it doesn't leak any information about the private client's data. So we want to change this whole thing into something that offers some privacy for the clients. Okay. So what we will do is, instead of the parties sending their whatever they calculated, we will mask it in some ways, okay? And hide this information. But then we're stuck in a problem, right? If what the bank is doing is that it needs to calculate things over the local model, then what does it do with this masked information? Think about this mask maybe as adding some random pad on top of the data. This data is useless. So the question is, we're stuck in this situation that the server gets masked information, and what does it do with this computation? And really what we want to enable the server to do is to calculate what it wants, but over the masked local model, and to still derive the correct answer from this data. Okay, so you can already sense that it's a little bit difficult, where we have a challenge here because we wanted to provide privacy, but we're somehow maybe hindering the ability to compute. And you know, like a magician in these shows that they say, okay, so blind me, this is like the mask, and then the person is going to be throwing swords at them, but no, we'll also spin it in it. So we want to make things harder also, you know, mask me, but do more. And then what do we want? Whatever we want to make it harder, we really want to motivate that by the application, not just for the show of saying, okay, I can do even more, but really things that happen in this scenario. And what are these things that could happen in this scenario that we want to improve? So first of all, these weights that they're calculating might be very, very long. So if they're longer than what we can encrypt, if you don't know what encryption is at this point, don't worry, but you can encrypt things of specific sizes. If it's too long, then you can't use simple techniques of encryption. So we have to do something else. That's one issue. The second issue is really, in the JP Morgan scenario, they have millions of devices that they want to get their information. And in each instantiation of this calculation that they want to do, they want to be looking at thousands of machines, okay? Thousands of little devices. The techniques that we have, most of them work in a quadratic time. So these things, even if it's 1,000, it's really doesn't really work. So we want to address this issue of a big system too. On top of that, we don't want to assume that everything is rosy and wonderful and that there might be some entities that are faulty. Most importantly, the server might want to learn some private information of these parties and might collude. Let's say it wants to learn the information of this party, maybe it colludes with these three guys and it can learn something. So we need to assume that bad things can happen as well. On top of that, some entities are phones. Now they don't look like phones anymore, but a phone is not always available, right? Sometimes you go to the theater, you turn it off, right? And now you can't participate in the computation either. So what do you do when devices drop off? Okay, and if they drop off before the computation, it's less of an issue. What happens if they drop off in the middle of the computation while things are going on? Can we deal with that as well? And then on top of that, we want to run this system multiple times. The server really wants to continuously learn the information from these little entities. And it has to be efficient, okay? If we are going for generic multi-party computations, this is not really going to provide us with a solution that can be deployed. Definitely not in this huge setting where the universe is 1 million parties and each computation is over 1,000 parties. Okay. So as I said, the paper was with multi-iterations. This is this big green thing that we say we want to run it multiple times. And I mentioned one-time setup because what happens is that in the solutions that existed up to now, they could run very efficiently once, but they have a very expensive setup that if you need to do it multiple times, it would kill you as well. So really, you need to set up the system and then have the interaction part be very efficient for many calculations. Okay. So now, this was the federated learning question. I'm gonna leave it for a second and I'm gonna talk to you about Sprint. Then we will come back to see how the techniques that we use help in solving these things. Okay, so as I promised you, a very good acronym. And I just randomly highlighted the letters that they would fit, but of course, the truth is that there is some better acronym that's connected to it, but I left this one. Okay, so Sprint comes to do a high throughput, robust, distributed Schnorr signature. And here again, I want to go slowly and explain what things are. So we'll just start with signatures. Signatures is something that we all know, right? You have a document and you sign it with a pen or whatever. But what is a signature in the digital world? There's a problem with just sticking a line of zeros and ones which represent my name, Tal Rabin. Because anybody can take this, let's say it says here, I pay the other tal $10, and then the other tal takes this thing and takes my signature and transfer it to, I will pay tal $100. That's only if she's not greedy. If she's really greedy, it'll be like 1,000. Okay, so this is very simple to copy. Of course, this is not anything that we can use in the digital space. So in fact, in the digital setting, we have what's called the digital signature. And these schemes of digital signatures have keys associated with them. There's a secret key and a public key. And the secret key, as its name implies, is something that you have to hold, secret, computer. And the public key is something that will enable others to verify your signature. So you sign with the secret key and you verify with the public key. Okay? Good. So now let's look at this digital primitive a little bit more. So what can you sign? You can sign anything that you want, documents. It enables you to establish secure communications. And today, also, you can sign cryptographic crypto transactions. You can say, I want to transfer 1 Bitcoin, you're a lucky day,
Very lucky.
to Rachel.
Wouldn't thought even.
Luckier than that. Okay, so you can sign these things. These signatures are special, not that it's important for this talk, but they embed the document into the signature so that the signature cannot be transferred from one document to another document or from one transaction to another transaction. They sort of hook everything together, and they can only be signed by the person who knows the secret key that correlates to the public key. So if the public key is in some bulletin board or public key infrastructure that it says that it belongs to Tal Rabin, I can sign when I have the secret key. But the interesting thing is that if Itzik steals my key, Itzik can sign in my name as well. So it's really critical that the secret key will be kept secret. And since now we've moved to this world that you also sign cryptocurrencies, these keys are really worth a lot of money, right? If you have 10 Bitcoins, that's a considerable amount of money that you don't want to lose. So where do we put this secret key? I don't know what Bitcoin is today, let's say 30, and I said 30,000, you have 10, that's $300,000. Where do you put $300,000 today, right? We barely like walking around with $100 bill in our wallet, right? Okay, so, and as I said again, anybody who gets the secret key, they're me, okay? There's no way that I can prove that it wasn't me who signed it. The secret key is me. So where do we put it? We can put it on our little phone. I don't know how comfortable anybody would be walking around with 300K on their phone. Not the best place. Okay, so you can put it on your computer. Okay, starting to sound a little better, but still maybe uncomfortable for some people, and we'll see in a second why. And another option is to write your secret key on a piece of paper and take it to the vault and put it inside the vault. You should put it in a water-prevented casing. You should laminate it. You should do a lot of things to it. Maybe you're afraid of fires. There are also things that you can put that are fire resistant. Whatever you do and you put it in the vault, the problem is that now it's in the vault. You can't sign either, okay? So now what do I want to do? Every time I want to do a transaction to buy a coffee at Starbucks, I run to the vault to get the key and I sign. That doesn't work. Okay, so let's go back to this solution. Okay, this looked of my three offerings sort of the best solution. But what do we have in this world? We have these hackers, of course, and as we know, they do go and steal keys. And in fact, a lot of money, cryptocurrency is stole by hackers, getting your secret key and taking your tokens. I know even cryptographers who've managed to lose their keys. So it happens, okay? So what can we do? How can we do? So what are the two properties that we want for this key? We want security and we want availability, right? Because we want to be able to sign when we need to, but we want it to be a bit more secure. So maybe we can take this secret key and split it into two keys, SK1 and SK2, with the following property that they sum up to the secret key, okay? Let's say my key is 10, I break it into 7 and 3, okay? My key is not 10, it's much bigger. Don't try to use that for my key. But it's 7 and 3, I put them, these are random. I choose these numbers at random, except for the restriction that the sum is my secret key, okay? And now I take and I put one key on one computer and another key on another computer, maybe on my phone or something, it doesn't matter, on two machines that I have, okay? Now this makes it much harder to get SK. I want you to know that if you see only SK1, because I said that it's completely random, I mean, I chose it at random and it was 7. When you see SK1, this doesn't teach you anything about SK, okay? And the same thing for SK2. So if you want to get SK, you really need to break into two machines. And as I said, that's twice as hard, okay? But now, I didn't just want to secure the key. I've already improved its security, which is great. But I'm in no better state than the vault, right? Because, in fact, what I want to do is that I want to sign with this key. I had two purposes. I wanted to increase the security of the key, and I wanted to make it more. So now, what do? I have two pieces, which I said are random. How do I now sign? What do I do in this setting? Well, one option is when I want to sign is to transfer SK1 into this machine. But this is not good because I go back to the situation of a single point of failure. If the attacker is lucky, or not even lucky, they're smart. I mean, they're just sitting in there and waiting for S1 to arrive. The minute that it arrives, it has SN full. So this is not a solution that enables me to solve my problem. I don't like that solution. So really what I want, in essence, is when I want to sign, the left side is what I would have done normally if the secret key was on my computer and I wanted to sign the message. This is the left side. This is standard. But what I want to achieve is that I can somehow create a signature under SK1 of the message that I want to sign. This is done on one server, on this server. And then I create something on this server, something, and then I can combine them in some manner to derive the signature that I actually want, okay? And I need to define, yes?
Sorry, I'm just trying to understand, what if we were to have two signatures, SK1 and SK2, without the property where their sum is SK, and we just require that it is signed by both SK1 and SK2? Is this fundamentally different?
Okay, that definitely is a solution. I didn't mention another property which I want to reject your solution, which is that I wanted to be the original format, that you would not know that it was created in this distributed manner. It's not because I don't want you to know that it was created in this distributed manner, but it's much more efficient. Now in your solution, I have to verify 2 signatures. If I need 100 signers, then I'm stuck even more. Now I have to verify 100 signatures instead of a single one. So it's an issue of efficiency, that we really want to have solutions that preserve the original structure and its efficiency. Okay, thank you. Okay. So now I need to do this thing. Did you do something or you're enabling it?
Fixing.
Okay. Okay. So now comes in the issue of the topic of threshold cryptography. And I put this little puzzle here because it's exactly this thing. You want to take these pieces and somehow create the whole, okay? And not an acronym. Rocco I continued the color pattern and I didn't mark anything in the words. Okay. So threshold cryptography deals exactly with this issue, that we take and we break key material, and that is even easy to do. I just showed you, I break it into 2 pieces that sum to the key. But the critical part that comes on top of that is that it threshold cryptography enables to conduct the cryptographic operations which we have, which are signatures, which I've spoken about, and also decryption, which is the complement. That somebody can encrypt something under some key, under some public key, and distributedly you can get the decryption of the message. Why is this interesting? It's the complement of this thing, because sometimes you want to keep information secret, that no one person can access it. So again, with this threshold setting, you take the keys, you encrypt under the public key, and you need a quorum of the parties in order to decrypt and see the actual message, okay? So it provides, again, this enhanced security and really provides privacy, and data can be accessed only if sufficient number of parties are there. And as I said before, threshold cryptography is also interested in preserving the original format of the signature or the encryption scheme that existed before. Okay. So it comes to offer enhanced security and availability of cryptographic keys. And this area of threshold cryptography, what I like about it is that it started in the mid to late 90s. And at the beginning, we had these stories of why it is practical and where it could be used and so on. But it was really very theoretical work. Nobody was thinking of implementing it, even though we had all the great stories of why it should be done and that it was a no-brainer. But these things didn't happen. But at the beginning, when we were doing this work, we really thought that it would have some practical uses, and we designed threshold schemes for the main cryptographic designs, RSA, DSA. We also were focused on the question of how do you generate the key? What I told you before is I have the secret key and I'll split it into 7 and 3. But that that means that the 10 was somewhere in some initial state in its full form. So it was a question of, can we generate the key without it being ever in a single place, ever known to anyone? And this result, by the way, which we had, I don't remember the year, for a distributed key generation, is in fact to this day still the standard that everybody is sharing keys. So it's very, very nice. For these schemes, RSA is not used so much. The application which now is driving a lot of the emergence of this thing is cryptocurrencies. RSA is not used often. And the digital signature, I forgot what that is. What? Maybe algorithm. Is now being implemented on elliptic curves, so now everybody's doing ECDSA. So it's based on some of these techniques, but they've changed them somewhat. But after that initial start with threshold cryptography and these yes we can type of results, we can do this, we can do that, really people moved into trying to improve the results and getting actual efficient solutions that could be implemented. And there's a lot of results that are doing this, and this in fact is the result. This is Sprint. This is the result that they're doing. And what is very, very nice, and somehow I'm always baffled, threshold crypto is a sub-area of what's called multi-party computations. And these things have moved into mainstream that it's crazy to me that you meet people who are in cryptocurrencies and they say, yes, we do MPC. Like, really, you do? And they speak these things. And Ron Wiener, who's a senator in Oregon, he wrote a bill for enabling students to do things with applications for scholarships for universities and so on. And in the bill, it says that you will have to provide MPC solutions for them trying to access the data. And if you cannot provide MPC solutions, you have to show that your solutions provide that level of security as MPC. And now also NIST, which is the National Institute of Standards and Technology, is going to standardize threshold cryptography. All these primitives, the key generation, the threshold schemes for specific schemes and so on. And this effort is now launching. And as I say at the end, I think it's going to be extremely exciting. And I think that, okay, I'll say that later. Okay. So now I left you on the hook with two solutions. You know, you're still in the federated setting. What are we doing there? And we have our cryptocurrency. What are we doing there? There it's a little bit more maybe clear. So this was where I left you, what we wanted to achieve. So let's eliminate some of the things and try to focus in on the point where the cryptocurrency comes to help us. So I'm not going to look at all these things, and I'm going to stay with these two things. I'm going to state that we transfer the inputs, the results of the computation in some masked form to JP Morgan, and that some devices can drop off. Sort of the setting, and I'm ignoring all the other things, though these techniques help in those solutions as well, but I just want to show you how here I can utilize these things in order to provide this. Oh, yes.
And you don't want to allow interaction? I was late. You don't allow it back and forth interaction.
Okay. I want there to be a setup in which parties can speak to each other. If there's no PKI, if there's a PKI is public key infrastructure, then I don't need the interaction, but definitely I don't want the little devices speaking to each other. If there are 1,000,
How about speaking to the
Server.
server? Can I speak back and forth or just
Okay.
send something?
this is an excellent question. As we allow devices to drop off, we don't want there to be multiple rounds of communication with the server. Why? Because that will reduce the quality of the information that the server collects. Who will drop off? The little guys will drop off. So it will bias your answers towards servers that are on all the time, or your laptop and so on. And that really gives a shift in the model that you're learning. So you really want, if the little phone is on and it sent a message, you want that message to be included in the calculation. Okay, of course, in general, it will be more biased towards machines that are on most of the time, but still, you don't want to miss a case where you did catch the little guy and then he drops off. So we want it to be a one-round thing, a one-round message. Okay. So what happens? We have these masks that were sent to the server, okay? And the server, in order to aggregate to compute this function, needs to be able to remove the mask. The mask cannot be part of the computation, because let's say that the mask was just adding a random number. Instead, my answer should have been 6, and I added a mask plus 1. This makes it into 7. It's not connected to my response as well. So the masks have to be removed. But as I said, we want to do one round, and a device can drop off between the time that it send the answer and by the time that the server wants to remove the mask. So the question is, what do we do in that case? So who will remove the mask if they drop off? Okay, so we're in this setting, we got the masked answers, and what we'll do beforehand is we'll use our threshold system, right? Here there's the 2 computers. And this will be for an encryption scheme, not for a signature scheme, but for an encryption scheme that you're going to encrypt to. So there's the public key. And what this guy will do is it will encrypt under the public key its mask. And that first time that it sends the masked answer, it will also encrypt this mask towards this system of distributed computers who are sharing SK1 and SK2. But then, if the guy for some reason drops off and we can't do anything, then, okay, one thing I want to say before. Why can't there just be one machine that the guy sends its encrypted mask to? Because that does not provide privacy. If the mask exposes the input that it sent to the server, then there's no privacy for the user. So because of that, you need to do the encryption under a system where no one can decrypt on their own. And they should be able to decrypt only when the guy fails, okay? There are some protections, you still don't learn their input. I'm not getting into that system. It's the whole design, you still will not learn. There's another second layer protection if this is decrypted. And then what you will do is these parties, this party will decrypt using SK1. I'll take the cipher. This guy will decrypt with SK2. And the same way that the signature was generated from the pieces, the decryption will be generated and you will get the mask, okay? So by integrating a small committee here, we enable to do the federated learning computation. Yes?
I think you're missing why you can't just have one single secret key, because in this way the mask is still exposed. Or like, are you saying you don't trust the servers And if there's one single server with a secret key, then they could like illegally decrypt and see the mask.
Exactly, that's exactly the issue. Because if you know the mask and you're colluding with this guy, I told you that this guy may not be nice. So if you collude with him and you get the answer of this guy plus the mask, you know the information. So it has to be in such a way that no one can do it. And we have some trust assumptions about the set of parties, that at least one of them is honest in this case. Okay. So now I'm going to show you a little bit of math just to get an idea of how these threshold signatures work. And in Sprint, we do what's called a Schnorr signature. And the truth is that the Schnorr signatures are genius in my mind. What they do is they take, for those of you who know, it doesn't, if you don't, doesn't matter to continue later. They take a proof, a zero knowledge proof of knowledge of exponent, and then they use non-interactive techniques to turn it into a signature. And it's just amazing how this thing was sort of found and discovered by Schnorr. It's really wonderful. And in fact, a DSA, the digital signature algorithm, was designed by NIST. And the reason that it exists is because Schnorr patented his signature scheme, and NIST does not use patented technology. So they had to design something else, which was really unfortunate because DSA is not as elegant and brilliant as Schnorr's original signature. Okay, so you have the public key, and you were working in a group, and G is a generator of the group. Don't worry about the math. So the public key is G to the secret key, okay? And you make this public. This preserves the privacy of SK. You cannot derive SK from the public key due to some hardness assumption. Then you get the message M that you want to sign. I told you that in signatures, the message needs to be embedded into the signature. And how does a single signer sign? They choose a random K, and they generate an R by raising the same G to the K. And then the signature is two elements. You just take a hash of the message in R, use SHA-256 to get this E, which is a number. You have to map it into the correct group. And then you just take and compute K plus E times SK. Now this S does not expose anything about SK because it's masked with a random K, which is committed to this R, okay? And this is Schnorr, super elegant, okay? Now, let's look how we do a threshold Schnorr, okay? All the time, I take my key and I split it as to SK1 and SK2. I'm eliminating where I'm working, what it is, and so on, just like that. Now, P1, the first server holds SK1 and the second server holds SK2. And now, individually, they will each choose a K1, a random K1, a Ki, K1 and K2, okay? And implicitly, we define K to be the sum of K1 and K2, okay? For the signature, we need R because we need to hash it for the E. So what do? Each one announces Ri, which is G to the Ki. This preserves the secrecy of Ki because of discrete log, okay? And then we just compute R, which is R1 times R2, okay? So now we have our R, which is based on the implicit K, which no one knows. Because P1 chose K1 and P2 chose K2. Great. Now, everyone can compute this E because you know the message, and now you know R, because everyone can see these two values, the RIs. So you compute the E exactly the way that you computed it up here. Okay? And now locally, S1 gives K1 plus E times SK1. Let's look at this thing. This thing doesn't reveal anything about SK1 because it's masked by K1. And P2 does the same thing. It gives K2 plus E times SK2. Okay? And now, let's just do S1 plus S2. What is S1 plus S2? It's K1 plus K2, which is K. It's E taken out times SK1 plus SK2. So it's E times SK. And we got the signature. Okay? In a completely distributed manner. Nobody knows SK1 or SK2. And we managed to create the signature. Okay, so this is a straightforward math, and as I said, it's so nicely derived because the Schnorr protocol is so beautiful that it also thresholdizes so naturally that it's wonderful. However, just doing this thing straightforward is still not efficient. And as I said, we really want to move these things into realms of efficiency. And to do these things, we used a lot of techniques to really up the number of threshold signatures that we can generate quickly. I'm not going to get into these things, but it uses super invertible matrices. It's not packet, it's packed secret sharing. And in a very, very interesting way, we even use SIMD technology, that we somehow do a lot of computations at the same time with the secret key. Really very nice things here. So this is what we did with our sprint paper. And just to summarize, I just want to say that threshold cryptography is in fact an extremely powerful technique that enables a lot of applications. I still think that we're sort of at the tip of the iceberg of where it can be used and how it can be applied. And about this standardization efforts, I think that when we get into them and a lot of criteria, which we would want the signature schemes and encryption schemes in their threshold form to satisfy, I think that there will be room for more original work and innovation that will be needed really to drive these things forward. So that's it. Thank you.
So we can take questions. Those of you on Zoom, we can hear you in the room. If you unmic and ask your question, you can also type it into the chat and I can ask it for you. And of course, those of you in the room, we can also hear you.
I have a philosophical question about names, which is why is it called threshold cryptography? It seems like thresholds aren't really used as much, and it should be named distributed cryptography. So where does thresholding come in?
So first of all, I agree with you that names many times are very, very bad. I described it as an additive setting, okay? But I want you to see that this additive setting, in fact, is very, very dangerous because I split it into two machines. What happens if the disk on one machine crashes and is gone? Now I lost my token. Nobody's gonna take my tokens, for example, but they're gonna be lost to me too because nobody can sign it. So in fact, we designed the schemes in a more sophisticated way. Let's say that we have three parties, okay? We distribute the key in such a manner that any two can sign, okay? And the threshold is 2 out of 3. So I'm justifying the name a little bit better, but yes, because we want to also really enhance the security, not just from attacks, but also from faults. And for that, we need the thresholds.
Just follow-up question, is there like a correctable version where if you lost something, you can recover it if there is enough,
Enough information to recover.
if there is enough, willing parties to recover, saying like, we lost one of our 10 shares, kind of, right, can we recover, assuming, the rest nine says, yes, we need to recover the 10 share. Is it correctable in that sense?
Yes. So I want to say something about threshold cryptography and about cryptography in general. In cryptography in general, we have assumptions. The minute that the assumption is violated, you're dead, okay? So when we do threshold systems like this, we say the threshold is T out of N, okay? If there are more than T faults, it's not gonna work. So let me give you a very fast recovery mechanism, okay? The way that I'm gonna do a threshold scheme, I'm gonna share it with a polynomial of degree T, okay? Amongst two T plus 1 parties, okay? And now if one, or let's say 3 T plus 1 parties, one party loses its shares, the others can be constructed.
If it's polynomials, then.
What?
If it's polynomials, then sure.
Yes, polynomials are like the magic word now, yes. So in fact, maybe all, I don't want to say all, but these threshold schemes, most of them use this kind of sharing to generate the threshold, and it has the nice property because it's an error correcting code. You can, you lose too many in one time, you're lost. Then the assumption's violated. But as long as you're not in that area, in that zone, you'll be fine.
Who decides how to split the secret key up and assign it to the different machines? Like who's making that decision-making power, and how do you know that they are not malicious?
Okay. So there are many, many questions in your thing. So first of all, if I'm gonna open a cryptocurrency wallet, okay? And I want my key to be in distributed form. I go and I tell someone, let's say Coinbase, they're not the best, but let's say Coinbase, that I want them to generate a distributed key on my behalf. And maybe I get one share of this key, okay? The way that it is done is using some algorithm, most likely the protocol which we designed in some years ago. Now, so I can give that kind of instruction and they will run a protocol which generates a key distributively. Why do I know that they're honest and that they're doing what I want and that they're not talking to each other and learning the key? This goes back to what I said, that we have assumptions. The assumption is that this does not happen. Is that 100% true? I don't know, okay? But we have to have some assumption. There is no a cryptographic scheme that I know of that doesn't make an assumption of one type or another, okay? Even your phone, when you're encrypting with it, there's an assumption that some mathematical problem is hard to solve. True or not true? We don't know, okay? So it's an assumption that they are doing what they're supposed to.
So you gave reasons why we wouldn't want multiple rounds of communication between the server and
this
the
specific
federation.
scenario.
But what if I want some kind of a stochastic gradient descent, some kind of back and forth between the central model and the models of the different parties?
Then you would need to add it. But as I said, first of all, you'd be losing in quality because every time you'd be losing the weaker links in this thing. So you could do some things. You could have interaction. It may help you to improve some aspects of the protocol, maybe to get them a little bit more efficient. But the issue of one party dropping out who's masked their information and it's already incorporated into the computation, you're not going to get around that. Because the information is aggregated from the leaves. And if that mask is stuck in there, you're gonna need this way to unmask it. So it could help in some things, but that thing of having the committee and using the threshold, the additional rounds is not gonna help. But you can do additional rounds. We wanted something that the computation is such that you're not reiterating.
Could you circle back to the distribution of SK? So you gave the example, you have this SK, you set up a wallet, say you're setting up a MetaMask wallet. And then you said that you mentioned Coinbase, but say MetaMask distributes SK amongst these different parties. The assumption is they distribute it and you don't know who these other parties are?
Okay, so I would do it in a different way. I don't want anybody ever to know SK, okay? So let's go,
But
Back
you
here.
you know SK, right?
I don't wanna know it either,
Okay,
sometimes you're your worst enemy,
sure.
okay? Okay, let's go back to this setting, okay? How would I set up the key? This is not a threshold, okay, I was asked. This is just gonna be a sum, okay? What will P1 do? P1 will just simply choose S1, SK1. And P2 will choose SK2, okay? And we will define S to be the sum of these two. It's an implicit definition, okay? It was never S. And it was never that S1 was given to this guy and S2 was given to this guy. S was created, okay? And also in these settings that you wanted to do threshold, you can still do it, okay? Here it's trivial what I said. But even in these stages where the shares are more correlated and you enable reconstruction, you can still create the SK in a situation that no one ever knew.
But I guess the creation of S is gonna be with the assumption of some trusted party like a Coinbase or a MetaMask or.
Okay. First of all, it's done distributedly.
Right.
Okay, it cannot. Now, true that today Coinbase, let's say if it's generating its keys, it's generating some parts here, some parts there, you can participate in the computation, okay? So that increases the chances that nobody knows the key, okay? But yes, some form of trust assumption. Maybe one day we move into the setting that we have some entities, right? Maybe Amazon participates and Google participates and maybe some non-for-profit that we trust more participates. And these parties do these things together. They will run a threshold generation key setup for things. These are future things that we may get there, but currently there is something that you want more, but you're not 100% getting. But maybe you are improving by a little bit. Maybe not the ultimate that we can achieve through these techniques, but you're getting something.
All right. Thank you, Speaker again.